to Week 12, Part 3 of EGM310, Observing Surface Motion. In this lesson, we will learn about how we can use satellite images to observe and measure the motion of different features on the Earth's surface. We are able to see relatively slow, large movements of surfaces from space. Because of the slight offset between different bands in different sensors, we can sometimes see faster movements, such as cars on a motorway or airplanes in the air, but what we're talking about here are large things like glaciers, as shown in the animation here, or permafrost. We can also track landslides from space, not normally the rapid landslides such as debris avalanches, although we might sometimes get lucky and be able to partly observe them due to the band offsets. But rather we're thinking of slower, long-term creep of slopes as something that we can monitor from space. We can also see ground subsidence due to changes in aquifers, how the ground actually lowers or raises in elevation due to changes in water levels underground. We can also observe volcanoes, how changes in magma storage within the volcano can cause the ground to move up or down. And finally, we can also observe earthquakes, not usually while they're happening, but we can use satellites to track displacements and see where and how an earthquake has had an effect. And to do all of this, we can use both optical and microwave sensors to observe motion using a variety of techniques. The first technique we'll talk about is what's known as offset tracking, which is normally done using optical images. To do offset tracking, we first need at least two images spaced far enough apart in time to be able to see displacements or motion. These images also need to be orthorectified, because otherwise the differences that we observe might be due to uncorrected geometric errors rather than actual motion on the ground. They should also be registered to each other, though there are ways to do this as part of the process of offset tracking. The basic method is as follows. First, we start with a small subregion, also known as a template or chip, in the first image. Starting from the same location in the second image, we search within a search space for that reference template by moving it around and comparing it with the second image. This process is known as template matching. Normally, we're looking for some sort of correlation between the two images. The higher the correlation, the more likely it is that we've found a match. The example here shows the reference chip with a size of 100 by 100 pixels and the search chip with a size of 150 by 150 pixels. It also shows the correlation peak at the location where the reference chip appears to have moved. We can estimate the correlation in a number of ways. Perhaps the most common is what's known as normalized cross-correlation, which helps to eliminate variations in illumination that might cause false matches. Another type of technique is what's known as phase or orientation correlation. This uses the image frequency rather than the image itself to do the matching. By doing this in a semi-regular grid in the image, we can estimate the displacement field of the image. In this example, taken from the ImGraph software, shows the velocity of Helheim Glacier in Greenland. This slide shows an example of results for Vavilov ice cap, an ice cap in Severnaya Zemlya in the Russian Arctic. Around 2013 or so, a portion of this ice cap began to collapse, flowing out into the ocean in rather spectacular fashion. The first image, here from March 2015, shows the glacier velocity at a point relatively early in the collapse. We can see ice spreading out from the main body of the ice cap, with the highest speeds, represented by red, somewhere above 10 meters per day. 1 year later, in March 2016, the ice lobe has expanded dramatically, with high speeds reaching well into the interior of the ice cap. We'll come back to some more examples of glacier flow later in this lesson. Recall that Aster has both a nadir and a backwards-looking camera. These two cameras observe the same portion of the Earth's surface with about 60 seconds of separation. We can use this to track faster motion, such as river flow, provided that we can find objects to track. The example here, which comes from a set of 9 different aster images that flew almost perfectly along the Lena River in Siberia, shows the variation in flow along nearly 600 kilometers of river in May 2011. A close-up here shows some of the detail that can be observed with these images. The examples here come from a 2013 study that demonstrated the potential of aster images for observing changes in river flow. Since then, similar applications to observe circulation patterns in ice-covered fjords have also been demonstrated. Moving away from optical imagery, we can also use synthetic aperture radar, or SAR, to observe ground motion. Remember that the phase of a signal refers to its partial wavelength. In this example here, we have a satellite sending a signal toward a target with the given wavelength that gives us 1, 2, 3 full wavelengths of distance, plus a small bit left over. This is the phase that is recorded by the sensor. For a radar signal, the phase has 2 different components. The first is a deterministic component, which comes from the distance between the sensor and the ground. The second component is random, caused by scattering from small objects, meaning objects that are smaller than the spatial resolution of the sensor. Fortunately, because this is mostly random noise, we can use 2 images acquired at different times or from different locations to remove the random component and recover the deterministic component, which gives us our distance between the sensor and the ground. If we know the satellite's position, this gives us the topography. As you can see from this image, this interferogram, so called because it's the pattern made by interference between the 2 radar signals, is ambiguous. It only tells us the topographic component within 1 full wavelength range. In order to actually calculate topography, we have to do something that is called unwrapping the interferogram, where we start with a point or points whose elevation we know, and then move up or down these fringes to calculate the true elevation. This is a process that is known as interferometric SAR or INSAR. If we have 3 images that meet certain criteria, or 2 images plus a DEM, we can calculate the deformation or motion of the surface between the first and the last observation. This is a technique known as differential INSAR, or D-INSAR. This gives us the deformation in the line of sight of the sensor only. In order to get multiple directions, we need multiple look angles. This process works great for small deformations. For large deformation, it can be hard to accurately compare the 2 signals and recover the deformation signal. One classic application of differential INSAR is in monitoring changes in ground elevation due to changes in terrestrial water storage. For example, this study from 2001 shows the seasonal elevation changes in Los Angeles as a result of groundwater pumping and replenishment. The changes observed here are tiny, less than a decimeter in size, but differential INSAR is particularly sensitive to these small changes, again depending on the wavelength of the sensor and how often we can get repeat images in order to observe these changes. We can also apply differential INSAR to study volcanoes. This example is from Ugashik Pulik, a volcano in the Aleutian Islands in Alaska. The last recorded eruption of this volcano was in 1814, and it has been generally quiet since then. Using differential INSAR, we can see the deformation pattern of the volcano as estimated by images from 1995 and 1997. We see a nice, clear, bullseye pattern of deformation in the center of the image here. This pattern is caused by the inflation of a magma reservoir by about 0.04 cubic kilometers at a depth of about 6 kilometers, resulting in an observed ground uplift of about 17 centimeters in the center of the pattern. Remember that underneath a volcano, we have a magma chamber that stores molten rock or magma that occasionally comes to the surface in the form of an eruption. Changes in the amount of magma can cause the ground above the magma chamber or the volcano to move up or down. Just like with groundwater changes, we can measure this from space. We can then use mathematical models to estimate the changes that led to the observed deformation, which helps us to monitor volcanoes and learn more about how they work. For this particular volcano, no eruption occurred at that time. Not all movements of magma result in eruptions, but it is nice to know that we can monitor and keep track of these things. Similar to optical imagery, we can also do offset tracking with SAR. Radar images have speckle. They don't look perfectly clear, and this is partly due to the influence of the same small scatterers that contribute to the random phase component that we talked about earlier. If we look at an optical image of snow on top of a glacier, we can see that it's fairly uniform. We have some differences due to topography, but other than that, there isn't much variation. In a SAR image, though, we see a significant amount of noise or speckle. We can use this speckle for offset tracking. As long as it's coherent from one image to the next, it gives us a way to track offsets between images. Unlike in SAR, this actually gives us a displacement in the image coordinates rather than the line of sight. Thus, we can recover a velocity field of two-dimensional motion using this technique. This does work better for larger deformations, though. In the interior of the ice sheets, where velocities are on the order of less than 10 meters per year, we normally have to stick with INSAR techniques in order to measure motion. This technique does provide an invaluable tool for monitoring the peculiar behavior of glaciers. A glacier surge is a periodic acceleration of about 10 to 100 times the normal background speed. These phenomena occur on glaciers all over the world, including in the high Arctic. The example here shows the development of a surge on Tunebræen, a glacier on Svalbard. In December 2016, Tunebræen began surging. We can see the increase in speed near the terminus of the glacier here, propagating up the glacier over time. Another example from Svalbard, this figure shows the development of a surge on Negerbræen, which began early in 2016. During the polar night, we can't use optical images due to the lack of sunlight. This is also true in times of heavy cloud cover. SAR satellites and offset tracking provide a way to continue to study and observe glacier surges even when we can't see them with optical sensors. In this lesson, we have discussed a number of tools and techniques available to study motion or deformation on the Earth's surface using both optical and microwave sensors. Which technique we use depends on our particular application and the availability of data. Optical data have seasonal and weather-related limitations that might make some applications difficult or impossible. INSAR is a powerful tool that can measure very small differences in elevation or very small motion, but it can also be heavily affected by changes in surface moisture or composition, and we can't use it to study larger deformation. Speckle tracking is great for larger deformation, but it too is very sensitive to the surface moisture and composition. I've included a number of links to videos here, including 2 on measuring ice motion from satellites and other imagery, as well as a longer explainer on INSAR and how we can apply satellite observations to study volcanoes. I've also included a link to an article about the surge of Tunebræen if you're interested in reading a little bit more information on glacier surges. That's all for this lesson. I hope you found it interesting, and if you have any questions, please don't hesitate to email me or post in the discussion forum on Blackboard. Bye!